All right, picking back up, this is the last thing with the derivative connections, or the extrema, the maxima, and the minimum. And this is a little packet that I like to call curve sketching. It's just like a little quick 2-pager. Shouldn't be too long. Anyways, let us go for it. Remember, we had the limit definition of a derivative. There's your secant slope. How you turn the secant into a tangent is applying that limit process. But we remember from limits, the limit from the left has to equal the limit from the right in order for that overall limit to exist. So for the derivative to exist, that's the slope of the tangent, the slopes from the secant on the left and the slopes from the secant on the right, they have to get closer and closer and closer to being the same thing. But essentially, the slope on the left has to match the slope on the right in order for the derivative to exist. And when that doesn't happen, there's a sharp turn or a cusp, and then the derivative does not exist. The derivative would be undefined at those specific points. So let's use this diagram for f, and let's answer the following questions. Okay, the first part, again, sorry for the document camera. I know it's not super great. It's like really frustrating how poor the quality is. Literally, I hit the focus button and then it's like is garbage, but whatever. Thanks, Round Rock ISD. All right, anyways, let's go for it. Are there any values for which the derivative does not exist? Yes, there's the sharp turn right here, and then there's also a sharp turn right here. So yes, x equals -2 and x equals +2 because we have those sharp, oops, can't spell, forgot the R. Because we have those sharp turns, the slope on the left and the slope on the right, those aren't the same. So we have this very abrupt change, which means that overall derivative isn't going to exist. Part B, are there any values for which the derivative is equal to 0? So are there any values where we have a horizontal tangent? Yep, it does look like right here. If I were to draw the tangent line, it would be perfectly flat. So yep, for that one, it looks like if I were to draw the horizontal tangent line at x equals 0, it would have a slope of 0. So yeah. Okay, I'm going to flip it over to the next page on my answer document, and I'm going to, I guess I can flip it. We're going to need to come back to this. I guess I'll flip it on this, and then I'll project the other one. Here we go. That should work. Okay, this particular function has an interval where its derivative is constant. What is this interval? And then what does the derivative function look like there? Estimate the slope of the original function on that interval. So yes, certainly it does look like there's a spot where the derivative is constant. Think if your derivative is constant, then your original function must have just been linear. Linear functions are the only things where the slope does not change. And yes, it does look like there is a piece to this graph, which is given to us as f. It does look like there is a piece of that graph which is linear. It's right here. So it looks like from, so 1, 2, 3, from -4 to -2, it does look like the slope is the same. So then the derivative would be constant. So from -4 to -2. That's the interval where the derivative is constant because it's a linear function. It's just a line. The slope doesn't change. What would the derivative function look like? Deriv looks like some horizontal line, y equals, and then whatever the slope of this horizontal line, which it looks like it goes down 2 over 1, down 2 over 1. So it looks like that derivative value is probably going to end up being this horizontal line. And then that horizontal line would be at -2, because that's what the slope of this line is, right? The derivative at this point and the derivative at this point, the derivative at this point, all of these infinitely many points on this straight line. The slope for all of those points looks like it's going to be -2. So your derivative function would be constant, and it would just be a horizontal line at -2. Estimate the slope of the function. We already did. Slope. It's going to be about -2. We can tell that just by counting the rise and the run. Okay, part D, on which interval is f prime positive? So we would say f prime is positive when f has positive slope. So that's pretty nice. That looks like, remember this is f, so it looks like it's got a positive slope in this interval. So from -2 to 0, and looks like from 2 to 4. And then on which interval is f prime negative? So where does that function have a negative slope? Well, f prime would be negative when f has negative slope. So that's going to be this interval right here, which is from -4 to -2. And it's going to be this interval from 0 to 2. Oh, sorry, I was totally off. Should be a pretty standard occurrence, right? Me being off the screen. Oh well, I try to not mess it up too much. Okay, here we go. Now use all that information and let's try to sketch a graph of this derivative. Well, we know what the derivative is going to look like for at least part of it. We know the derivative is going to be constant. So everywhere from -4 to -2, that derivative is just straight up constant. So we got here and then there, close enough. So we know the derivative is constant. It's just a horizontal line in that interval. Now remember, going back to the part A, the derivative does not exist at those points. So it should be an open dot, right? The derivative does not exist at that specific point. So we've got part of it done. That's nice. You could leave this one as open or you could close it. Honestly, that doesn't really matter. But this one for sure needs to be open. Now let's think about kind of what some of the other slopes would be. If you're looking at the graph, this middle segment looks kind of like a parabola. It starts off with a positive slope, then it has a 0 slope, then it's got a negative slope. So for sure I know the derivative is going to go through this point because the slope at 0 was 0. But then on this interval, between -2 and 0, my slopes look like they're positive. And they start off with like a slightly bigger slope, and then it's smaller, then it's smaller, and then it's 0. And then here, they're like slightly negative, and then it's getting bigger negative. But this kind of looks like, if you were to extend it, that kind of almost looks like a quadratic. And so it would kind of make sense for the derivative to be linear. So let's think about something. I could kind of say, okay, well, I don't really know exactly what that slope is. Maybe it looks something like this, though, where it should be kind of close to being linear. Okay, and then we got the last little piece that we still need to define between 2 and 4. Let's see, again, that looks like it could be quadratic, like just the right side of a parabola, but it looks like the slopes start positive, right? It's definitely not 0 right there. That's undefined slope. But it looks like kind of right at this point, it starts with a fairly decent positive slope, and then the slopes are going to get bigger. So this derivative starts off above the x-axis, and then it's going to get bigger. So it's going to move away from the x-axis. So I don't know exactly what number it's going to start with, but I'm just going to say, hey, it starts here, and then maybe it just gets bigger, and it goes over. Let's do something like this. Sure. Again, like this kind of has some room for flexibility. It doesn't have to be point for point precise, but that would be a decent sketch. Remember, sketch means it doesn't have to be point for point precise. You just have to generally get the right shape. For sure, the derivative was constant because your original function was linear. Then the derivative was positive, switched over to negative. You should have this x-intercept right here at the origin for sure, and then that other part should always be positive. So that section between the 2 and the 4 should be above the x-axis. Okay, here we go. Part E, which I believe is the last part for this particular question, and then we can flip over to the example 2. It says, on which interval is the second derivative negative? Remember, second derivative is the slope of f prime, right? That's your second derivative. Second derivative is just the slope, the derivative of the first derivative. So let's see, it looks like this graph has a negative slope. For this particular piece here, the slope of f prime is 0. So your second derivative for this interval would be 0. Here it looks like your second derivative would be negative. Here it looks like your second derivative would be positive. Okay, so let's see. F double prime, second derivative, that's the same thing as slope of f prime. And we know slope of f prime is negative for the interval -2 to 2. If you wanted to write it in the interval notation, there you have it. Okay, I'll flip it over and let's do the next example, example 2. Oops, can never get this the correct orientation. Oh well. Below is a graph of the derivative g of x. Ooh, so this one's different, right? The previous question gave me the graph of f and then asked me stuff about f prime. Here it is giving me the graph of g prime. So make sure you always pay attention to what the graph you are given is labeled as. Is it giving you the original or is it giving you the first derivative? Sometimes it may even go crazy and give you the graph of the second derivative. That's kind of rare, but it could happen. Always pay attention to what the graph is labeled as, because if you kind of mess it up, everything is going to just be wrong, and we don't want to be wrong. All right, so this is the graph of the derivative. Assume this is the entire graph, so that's great. Use it to answer the following questions about g. All right, cool. On what intervals is g increasing? Well, I know g is going to be increasing when g prime is greater than 0. Please do not say this interval and this interval, right? That's where g prime is increasing. If I want g to be increasing, that means I would want g prime to just be greater than 0. So let's see, that would be this interval right here and this interval. So I can say, hey, g is going to be increasing when g prime is greater than 0. So whenever this graph, g prime, is above the x-axis, we can go ahead and get this answer. Now, these numbers aren't exactly labeled super great. I'm just going to approximate. I'm going to say like that one. Let's see. Let's count this at about. Oh, these units aren't really labeled super well. Okay, so let's say that's 1, 2, about 3. So I guess like maybe like 2.9 or so, wherever that x value is. We'll just label it as negative 2.9. Negative 2.9, and then all the way to this one, which is negative 0.5, and then also 1, 2, 3. So between 3 and 4. So let's just call that one 3.5, just for the sake of simplicity. And then we could put a bracket on the 4 since that point is above the x-axis. Let's do decreasing now. So we know g would be decreasing when g prime is less than 0. So where is this graph beneath the x-axis? Well, it's going to be everywhere else. So we could put from your negative 4 to your negative 2.9. And we could say from that negative 0.5 all the way to your 3.5. Okay, so if you want g to be increasing, you just want your derivative to be positive, which means above the x-axis. And then here for the negative, you'd want below the x-axis. So answering questions about g when given the graph of g prime should be pretty easy. You just have to really follow the logic. Part C, suppose g of 0 equals 0. Is the function g ever positive? How do you know? Well, let's think about this for a second, right? Think about this interval from negative 1/2 to 0, right? It looks like g prime is less than 0 for this interval, the negative 0.5 to 0. So we know the function g has a negative slope. G has negative slope for that interval. Let's think about this graph. If I know g of 0 is 0, and I know, let's say here, that's negative 1, here's your negative 1/2. I know the function g has a negative, sorry, I'm off the screen. That is my bad again. It's like always struggling, sorry. So I know the derivative is negative since it's below the x-axis. That means g has a negative slope. Well, if this point ends up at the origin, which it tells me, and it has a negative slope, kind of work your way backwards. The only way to have a negative slope and then end up with the point at the origin, well, if you kind of work your way backwards, the function must have been above the x-axis, right? That's the only way that would make sense, right? This function, it doesn't really know, I don't really know exactly what it does, but in order for this function to end up at the origin, it had to have had a negative slope, and since it had that negative slope, I know it must have started off above the x-axis. All right, so let's see if we can write an answer that makes sense. So let's go for it. Yes, we do know for sure. Is the function ever positive? Yes. We could say something like g is decreasing from negative 1/2 to 0 Therefore, come on, pencil. Therefore, g of negative 1/2, oops, I can't spell, oh my gosh, must have been greater than 0 for g of 0 to be 0. Hopefully that makes sense, since you want the graph to end at the origin, and you know in that little interval, we know the function was decreasing. Since it was decreasing and it ends at 0, it must have started above 0, right? You must have started with the positive value and then it decreased down to 0, right? Just kind of just logically working your way backwards. Okay, part D. How many inflection points exist? And then label them on the graph of G prime. Okay, well, let's think. G has point of inflection when G changes concavity. That's the definition of a point of inflection. You're going to have an inflection point when the function changes concavity. That's great, but please don't say this point, right? Because this is not the graph of G. Remember, this is the graph of G prime. So right here, where it looks like it switches from concave down to concave up, like it looks like that's a tempting answer to say 1 right here at x equals 0, but that's not right, because that's not the graph of G. We need the graph of G prime and how we're going to somehow figure out where the inflection points are on that. Well, let's think about it. I know G has a point of inflection when G changes concavity. That's the same thing as saying your second derivative changes sign. And if your second derivative changes sign, that means your first derivative changes slope, or it changes behavior. Because remember, the second derivative equals the slope of the first derivative. So if you want G to change concavity, that means the second derivative has to change. Well, that means the slope of G has to change. So you're going to look for wherever G prime changes from increasing to decreasing, or from decreasing to increasing. And what we call those points are maximums and minimums, right? We know if your function changes from increasing to decreasing, that's called a max, and decreasing to increasing, that's called a min. So your relative extrema, your minimums and your maximums for the first derivative, those are going to be the places where your second derivative changes sign, right? If your first derivative changes slope, then your second derivative changes sign. And then that is going to correspondingly cause a point of inflection for the graph of that original function, right? So the extrema of G prime are the points of inflection for G. So therefore, yes, 2 points of inflection. They're not really labeled, but I guess we could at approximately. We have this one. I'm just going to say that one's going to be about -2, and then I'm just going to say this one's about 2. So I'm going to say about -2 and 2. But there's definitely 2 points of inflection, which is what the question wanted. And then here we could label them point POI, this specific x value, and this specific x value. The places where your first derivative has a max or a min, those are the things that end up being points of inflection for your original function. Kind of a little bit weird, but think about it like this, right? This is your first derivative. Over here on the left, this graph has a positive slope. So I know everything on this interval, G double prime is positive, right? Because this slope is positive. Then everything in between here, G double prime is negative, because the slope of G prime is negative. And then over here, this graph has a positive slope, so I know G double prime is positive. So it's concave up, then it's concave down, then it's concave up. So we will have a point of inflection at those values where G changes concavity, which happen to be at the maximums and the minimums of the first derivative. Kind of weird, but not too bad. Just got to really follow the logic. And then the last part of this little mini worksheet / packet is just some matching. It gives me 6 graphs and 6 derivatives, and then all I have to do is match them. Well, let's do it. The first one I think looks pretty easy. I guess you would kind of have to be careful. These two are a little bit weird. Here, I'm going to number them. How about we just do 1, 2, 3, 4, 5, and 6, just so that way we can kind of be on the same page. All right, so the graphs 1 and 4 actually are going to have derivatives that look fairly similar, right? I know, hey, this is linear, and I know if the original function is linear, then I know the derivative should be constant, right? And specifically, this is going to have to be a positive constant graph. This one's going to be kind of the same, right? This graph is linear. It's just broken up into the two pieces. And so really this one, y is going to be linear. And so your derivative is going to be constant. But then this one's going to have an issue at x equals 0 because it's got this weird little discontinuity. It's got that weird little break. That one's going to have something weird happening. There is no slope technically at this point because it's not even continuous. You can't have a slope if the graph isn't continuous. But for sure we know, hey, this one on number 1, it looks like your y equals x, so it looks like your derivative should be 1. So I'm thinking that looks a lot like the graph for b. Now, the answer for number 4, right, is going to be similar. Like this looks like it has a slope of 1, and this looks like it has a slope of 1, but there's no slope at this value where x is 0. So that's really going to be this graph f, right, where it's 1 everywhere except for when x is 0. So that one is f. So 2 down, 2 to go. 2 looks like your original function could be something that's like negative quadratic, so then your derivative should be something linear. It should be a negative linear function. All right, so we got b and we got f. I'm going to cross them off. It looks like something that could be pretty close to negative and linear. Looks like d. And then let's see this one. Here you have your slope is like a negative 1, and then over here your slope is a positive 1. So really this one is kind of linear, except your constants are going to be two different values. Here this derivative is going to be constant and negative, and here this derivative is going to be constant and positive. So this one's going to correspond to your graph A. And then let's see, the equation for 5, that kind of looks like a cubic function. And so we could guess like, hey, if your original is cubic, we could kind of guess that the derivative is quadratic. Another way to kind of make sure is like this for sure is always positive. It should have a slope of 0. Slope equals 0 at x equals 0, so that means you should have an x-intercept at the origin for the derivative. But for sure, if we think this one looks cubic, then the derivative should be quadratic. That makes sense. So then logically, we should be able to conclude that E is the graph for 6. Let's make sure. Here, it looks like your original function is linear, so your derivative should be constant, and it should be positive. Right? It looks like that derivative is constant for the left side, but then here on this other piece, it looks like your original function could be something quadratic, or maybe that's something cubic. It's really hard to tell. Like maybe like this and this look kind of the same, but for sure we could tell the derivative is going to have to be positive. And then we could kind of guess that it's going to be, hey, if this looks like a cubic-ish shape, you really can't tell if it's cubic or if it's quadratic. But luckily, we have only the one answer left, the constant linear part for the left, representing the slope of this line that never changes. And then it looks like, yeah, that probably must have been cubic, because over here it looks like the derivative is quadratic. So there we have it. We did the matching ones. You're not really ever going to have stuff like that again, but it's kind of a little bit nice, I think. Anyways, hope you enjoyed. I know this lesson is weird. All this stuff with these different derivative connections, and then the extrema and the maximins. Let me just quickly kind of go back through and just summarize everything high level for you. What's important, right? Because there's a lot of stuff going on. Let's just summarize and let's get the important stuff. First of all, the fun chart is something that you want to know. Okay, so let's redo the fun chart, and then we'll kind of talk about a couple other things. Fun chart. Again, I would definitely, if you're not taking notes, you should probably at least take notes for this, because this is key conceptual stuff. If your first derivative, let's see, f prime, that's the same thing as slope of f, and then f double prime, that's the same thing as the slope of f prime. So that's great. Let's logically kind of fill out this fun chart. Once again, now that we've all finished with both of these notes packets, let's do it. If your first derivative is positive, that means the slope of f is positive. That means f would be increasing. Right? So if the first derivative is positive, that means f is increasing. If your first derivative is negative, that means the slope of f is negative. That means f is decreasing. So when you're taking a derivative, going down one layer and taking one derivative, that's going to end up telling you the behavior, the slope of the graph, right? Increasing or decreasing. Now going down 2 layers is a little bit harder, but let's try to follow the logic. If the second derivative is positive, that means the slope of f prime is positive. Well, that means f prime is increasing, right? Positive slope is the same thing as increasing. And if f prime is increasing, that means the slope of your f function, the slopes of that original function are getting larger. And if your slopes of that function are getting larger, it's going to create this upward curvature to the graph, which we call concave up. So second derivative positive means your first derivative is increasing, which means the slopes for your original function are getting bigger, which means upward curvature, concave up. And then if your second derivative is negative, that means the slope of f prime is negative. Therefore, f prime is decreasing. And if f prime is decreasing, that means the slope of f is getting smaller. And if the slopes are getting smaller, it's going to create the downwards curve, which we call being concave down. Okay, that's really good. Remember, you have this first derivative sign chart. You find all the critical points. We'll just say A, B, C, D. Say it's positive, negative, positive, positive, negative, right? If the first derivative is positive, that means your original function is increasing. Let me do one more, just for fun. So we'll do E, and we'll say that's negative. If your first derivative is positive, that means increasing. When your first derivative is negative, that means decreasing. So you can answer anything you want to know about increasing or decreasing. You'd say like, hey, f is increasing when f prime is greater than 0. Then you just tell me what those intervals are. You could say f is decreasing when f prime is less than 0. And you tell me what those intervals are. And then you could also use this first derivative sign chart to find the max and the mins. Like, hey, if the derivative changes plus to minus, that means it changed from increasing to decreasing. That means that point would be a max. Vice versa, if the derivative changes negative to positive, that means f was decreasing to increasing. That means that's a min. Here there's no change, so that would be a neither. Here there's a max. Here there's no change, so that would be a neither. Right? And you could classify your extrema relative max or min at x equals, and you could say by first derivative test, right? The interpretation of the sign chart telling me how that derivative changes and that correspondingly produces a max or min. That is the first derivative test. If you don't want to say first derivative test, you could say, okay, f prime changed positive to negative, therefore f changed increasing to decreasing, therefore max. Or it could say f prime changed negative to positive, therefore f was decreasing to increasing, therefore minimum. Now you don't have to write out all of this stuff. All of the stuff that I just boxed, that is literally what the first derivative test tells you. So you could either write out the sentences, or you could just say by first derivative test. You don't have to do both. If you cite the test, you don't have to tell me what the test says. But if you're not going to cite the test, then you would need to write some type of a justification in order to make sure you're getting all those points. Right? But your first derivative, that's how you answer increasing and decreasing. And then it's also how you find max and mins, and that process is called the first derivative test. Now we know the second derivative is also useful. Let's just do kind of the same thing. Let's say A, B, C, D, and E. We'll just do the same thing. Plus, minus, plus, plus, minus, minus. And again, these are all the critical points. Your critical points, or your stationary points, those are all the things that might be maximums or minimums. It's the collection of all those important values for the first derivative. The important values for the second derivative, there's no name for them, but those are the things that might be points of inflection. And then you'd still have to test, right? If your second derivative positive, that would mean concave up. If your second derivative was negative, that would mean concave down. So here we'd have a point of inflection. Here we'd have a point of inflection. Here not, because it's concave up on both sides. Here not, because it's concave down on both sides. But anywhere your function changes concavity, i.e. your second derivative changes sign, that would be a point of inflection. And then you could answer questions. You say f is concave up when your second derivative is positive. Then you say therefore, fill in the blank with the intervals. You could say f is concave down, like a frown, when your second derivative is negative. Therefore, fill in the blank with all the intervals. And then your last thing, you would say f has point of inflection when, and there's a couple different things you could say. You could say f changes concavity. And if you've already done the intervals of concavity, that should be pretty easy. Or you could also say the second derivative changes sign. Or just because if that's not enough, you could do more. Or you could say f prime changes slope, or it changes behavior. Or you could even say has extrema, right? Having extrema is the same thing as changing slope, changing behavior. Anyways, any of those three is fine, right? But it's not second derivative test. That is another way to find mins and maxes. If you want to justify points of inflection, one of these statements is fine. I would just recommend always just do f changes concavity or whatever. If you're talking about g, then g changes concavity. But then you would just say, okay, therefore at x equals, and then you just list out the values. So we have the first derivative, and it tells me about increasing and decreasing, which we use to find mins and maxes. And then we have the second derivative, which tells us concavity, the shape of the graph, which we use to find points of inflection. Right, and remember, critical points are only for those important values from the first derivative. Those important values for the second derivative, those are also key, right? Because those things may be points of inflection, but there's no word really that stands for them. Just think about them as being special values for the second derivative, but they're not critical points. Critical points, stationary values, those are all things specifically that could be max or mins. So those are the things that make the first derivative 0 or undefined. All right, so that's a lot. Hopefully that makes sense. I'm definitely going to try to make sure to go through all this with you guys again in class, because conceptually this is going to cover a lot of the Calculus 1 stuff you see in this year, right? And if we don't have the fundamentals down, a lot of the rest of the stuff is not going to be super fun. Anyways, there it is. Hope it makes sense.